and equal to 0 and m equal to 0 at the same time is not allowed. If m and r all 0, you see that there's no field exists, okay? If you keep m equals 0, then everything goes away. So you cannot have n equal to 0, m equal to 0 at the same time. But for the field expression, for the z component of the field expression, here you cannot set p equal to 0. Okay, the minimum value for p is going to be equal to 1. Now it's a time to discuss the dominant mode for a rectangular cavity. Because you will have Tm and T mode, both of them are in the cavity, okay? But for the rule for Tm mode is that you cannot have any of the m equal to 0, and the p equal to 0 is allowed. So the dominant Tm mode is going to be Tm110 mode, okay? But for T mode, you cannot have the m and n equal to 0 at the same time. But p, the minimum value for p has to be larger than 1. Okay, so the dominant mode inside the rectangular guide will be Tm110, Te101, or Te011, depending on the value of a and b, the value of a and b in the first two indices. Okay, if I want to pick this one, basically A has to be larger than B, and if I want to pick up this one, then B has to be larger than A. So, for example, if I have a rectangular oscillator with A larger than B larger than D, A is the largest value. So this means that you will have a dominant mode. For the Tm mode, you're going to have the dominant mode, that is Tm110. But then for Te mode, the dominant mode is going to be Te101, okay? Because the largest value is A, so the first index you choose is going to be, for Te mode, is going to be the 1, okay? Try to remove the small the inverse dimension from the B, okay? 所以呢，这个你在讨论这个 dominant mode 的时候呢 ，you need to know the value of A, B, D, so that you can choose the right mode to discuss. Alright, so 所以这个有点就是比大小的一个概念。But then want to know how to calculate the cavity Q, okay? Alright, so for the dominant Te mode, suppose that you have A larger than B larger than D, then the dominant Te mode is going to be Te101 mode. There's no variation along y direction, but you have one standing wave lobe along x direction and one standing wave lobe along z direction. That is how you read this index. Okay. Alright, so you can write down all the field expressions like this, and then with the field expressions, you can calculate the average stored energy through this energy density calculation. Okay, don't forget that when we talk about average, there's a factor 2 here, but in fact, well, this is a total magnetic energy. Okay, the total magnetic energy calculated from this one and this one, if you add them together, it's going to be the same as the total electric energy. So let's do that calculation separately. Let's first calculate the total magnetic energy, and then calculate the total electric energy. But don't forget the factor 1/2 in front of that. With those few expressions, of course, you can finish this calculation by yourself. Okay, just do the volume integration. And then you end up having the total electromagnetic energy in this calculation. Okay, and of course you can start to calculate the loss, the ohmic loss, so that you can calculate the cavity Q. Well, for the cavity Q, you have an expression that is. For the cavity Q, you have an expression that is omega, average energy, power loss. This is the frequency. Now you finish your calculation for this. now you have to calculate the power loss in this cavity. So that is related to the ohmic loss on the surface of those 8 surfaces, 6 surfaces, 1, 2, 3, 4, 5, 6 surfaces. Okay. So you want to know the tangential component of the magnetic field. This one and this one. Okay, this one is this one. For S component of the magnetic field, you will induce surface current along this direction. And then you have 1, 2, 3, 4 surfaces that will have surface current associated with this one. And for this, the Z component of the magnetic field is along this direction. So you have this surface, and the surface in the back, and the surface in the bottom. That has the surface current associated with this term. So you have 4 surfaces that you have to calculate the ohmic loss associated with this term. Another 4 surfaces associated with this term for the surface current. So totally, you need to calculate 8 surfaces for the surface current. Okay, so let's do it. Previously, we knew that the surface loss per unit area is given by this expression. Okay, so you need to identify the surface current from this surface magnetic field, Hx and Hz. Each accounts for 4 surfaces. For example, for this Hx, you have 2 surfaces along Z direction. Okay, and then Hx, you have 2 surfaces along Y direction. So here and here you have 4 totally 8 surfaces that you need to do the calculation. Okay. Now same thing for the Z component. For the Z component of the magnetic field, you have another 4 surfaces for your calculation. So you have this term and this term. So you need to go through those surface current calculation to determine the ohmic loss on those surfaces. 注意，你一个这个 box 的话呢，有6个面，但是呢 surface current 的计算呢，要计算到8个面。OK， 每一个 surface magnetic field accounts for the loss on 4 surfaces。走一圈，在这里走一圈，有4个面，一样，在这里走一圈有4个面，总共有8个面在那个地方。Even though a rectangular box has 6 surfaces only. So once you do the calculation, then you figure out the surface loss, ohmic loss on the surface. Then you are ready to calculate the cavity Q based on this equation. So this is sort of a step that I guide you through to do the calculation for cavity Q. Then the final topic is to just change the geometry into a rectangular resonator. Okay, now we have a cylindrical resonator like this, and you knew that they were going to look into the Bessel functions. Okay, so just a little bit distortion, then we can generate such a cylindrical resonator. And then you knew that there's an important axis around Z direction because that is the obvious direction in this geometry. So the TE and TM wave are well defined. Okay. Now you'll be expecting that you have the standing wave along Z direction. So same thing. Let's write down this expression. Suppose we have a TM wave. With the TM wave, you have Z component of the electric field. Then you have standing wave oscillating along this direction, so it's a matter of choosing the sign to construct the field. While for Z component, it's a normal component, so you will be expecting cosine dependence. So we write down cosine dependence from this expression to this expression. And on the boundary, you want to have maximum, so beta is converted into Q pi over D. All right, is there any question about this? All right. And so you end up having this expression, then everything becomes simple, right? Because this is the dispersion relationship you have before. Now H is relevant to the determine this color frequency. H is the transverse eigenvalue, remember that? And this is the propagation constant along z direction. All right, so I want to remind you that the boundary condition, again, when r equal to a, then the z component electric field has to go away. So this H value is determined from the zeros of the Bessel function, x and p. Okay, so for example, the first value is here, x01 associated with this Bessel function of the first kind of zero order 0. Then you have x01 equal to 2.405. And the second value is here, and the third value is here, fourth value here. But if you have n dependence, that is starting from 1, n plus n comes from this angle dependence. This n can be 0, can be 1, can be 2, can be 3. That accounts for the standing wave propagation of the wave along phi direction. This one and this one, okay? So when you put n equal to 1, then you'll be looking into this G1 function. So you also look for the zero crossing to set the boundary conditions. All right. So now for the z value, for the beta value, is set it to be q pi over d. Then this value is set by the zero crossings of the Bessel function. Then you can calculate the resonant frequencies of the resonator, right? Given by this equation. Now, still you have three indices for this three-dimensional resonator. Previously, for the rectangular box, rectangular oscillator, we have N and P determine the resonant frequency. Now you have MPQ determine the resonant frequency. And N, the first index here refers to the mole number along phi direction. And P is the mole number along r direction. Okay. And Q is the mole number along z direction. Okay. Previously we choose this Q to be inside cosine. So Q, the minimum value of Q can be 0. Okay. And minimum number of this n can be 0 as well. So you see that the dominant Tm mole inside such a cylindrical oscillator is Tm010 mole. OK， 这个是 Q 可以是0，因为在 z 的方向上头你选择了一个 cosine 的键。那当你设定 n 等于0的时候呢，这前面第一个 index 就是0。So you have the dominant Tm mole that is Tm010. Right. So everything's more or less straightforward. Now it comes a time to calculate the field and also the loss and then the capital Q. So you need to write down all the field components. Okay. So suppose that we choose the dominant Tm010 mole, then you see that there's no variation along phi direction and there's no variation along z direction. The field pattern is quite straightforward. It's one standing wave flow along r direction. That is the Bessel function of the first kind of the order 0. So you have z component electric field along dictated by the G0 term. So the field expression is quite simple. You want to have two terms, Ez and H phi. And they are all phased by 90 degrees. Okay, this is a characteristic of the field inside a resonator. The field, H field and E field are all phased by 90 degrees. Therefore, you don't have an average power for the standing wave. Okay, you have power inside, but there's no average power for the standing wave from pointing vector's point of view. 所以它的这个 mole field 非常简单。 在 z 的方向上头呢没有变化，因为第三个 index 是0 ，OK。然后呢，沿着 r 的方向有变化，因为有一个 e 在这个地方，沿着 phi 的方向上头没有变化，很简单的一个这个 mole 的 pattern，OK。Alright， 所以based on this the mole field, we can now calculate the quality factor, and the calculation is particularly simple because the 你现在只有2项，很简单。这两项存的这个能量呢是一样多 ，OK。所以你可以算这个，然后呢直接乘以2，或者算这个直接乘以2，就是它里头总共储存能量。Okay, so let's do the calculation. Well, you can calculate this, or you can calculate this, and multiply it by a factor 2 to get the total average energy stored inside. Alright, so so this is the volume integration. So you'll be calculating the GA0 square. Okay, so this is the 微积分的范围。you can finish the calculation. For the power loss, then you identify that there's a phi component of the magnetic field. 你如果有 phi component magnetic field 在这里的话呢，你有几个面？前面的一个面是 tangential define this the phi component magnetic field is a tangential component， 或者还有一个面，旁边还有一个面，总共3个面在那个地方。This phi component of the magnetic field will induce surface current。你如果有这样子的这个magnetic field 的话，那你的这个 surface current 在这个 r 等于 a 的面上头的话，就是朝着这个方向在流动。Okay. So you have basically you have the 3 surfaces you need to take care of it. So for r equal to a, you have 1 ohmic power loss along the surface r direction, along this surface r direction. Okay. r 的方向是这个方向，所以一定是这个方向。OK。那另外呢，你有2个面在这个上头是 z 的 surface， 所以 have z surface plus minus z direction. You have 2 surfaces, alright. So you can also calculate the ohmic loss associated with them. Once you have these 3 terms, 1, 2, 3, then put it into a formula right here. You have the capital Q. So this is how you do the calculation for capital Q. Once you have the capital Q, you know how good this cavity can store energy. Okay, and then you know how well you have to control the excitation frequency so that the energy can be deposited inside. So this is the what cavity Q will tell you. 那在这里都是还蛮理想的状态，有些应用的话会在这上头挖一个洞，这时候呢，你的 power loss 呢，你就是必须去算一下这个从这个洞里头辐射出去的 power 有多大。Okay, and now we only calculate the ohmic loss associated with it. All right. I think this chapter appeared to be more or less simple. 有没有问题？到目前为止，我们讨论这个 Tm mole, and then we can continue our discussion for Te mole. For Te mole, you'll be talking about magnetic field component along z direction, right? So let's write down the expression for the z component magnetic field, and then try to determine the value for beta from the boundary condition. And this is normal component of the magnetic field on the z surface. So you'll be expecting that this is the I'll give you nothing, because z component, the normal component of magnetic field at the boundary, has to be equal to 0. Tangential component of the magnetic field on the metallic boundary has to be equal to maximum value. So you'll be expecting that, hey, I just write down beta here to be sign dependence, this is normal component of the magnetic field. Okay, side dependence, and then at the boundary, the value has to go to 0. So beta value now is replaced by q pi over d. This is a little bit boring because all the steps are going to be the same, except that you just sort of adopt the basic concept and then write down all the field. 所以这个逐渐变成一点机械式的这种计算。OK， 那基本的物理概念的话，在第一个小节里头介绍还蛮多的，希望你能够留下印象。Alright, now, but the boundary condition for the electric field at R is equal to 0 for the tangential component of the electric field. So when you do the calculation for E phi, then you end up having a calculation for the derivative of the Bessel function. Okay. So if you set R equal to 0 and take out this phi component of the electric field, then you'll be looking into the zeros of the J prime Bessel function. Okay. Now J prime Bessel function 是 J 的 Bessel function 的微分，当它这个微分的值等于0的话呢，是掉到这些地方来。OK， 那最接近这个地方的这个最小的这个 zero crossing 的 value 是 x prime 11 equal to 1.841。OK， 所以呢，这个会来定义你的 resonant frequency。Alright, so at this boundary condition, setting at r equal to 0, E phi equal to 0, that will determine this h value. Okay, this is the transverse eigenvalue, if you still remember. Previously, when we talk about the slack work guy, this h is equal to ky, if you still remember. Okay, so this h value is determined by the zero crossings of the derivative of the Bessel function. So it's given by this expression. And again, this is a little bit routine, 因为我们已经知道所有的这个解的方法，来从这个 dispersion relationship 过来的话，这个 h 的值由这个 s 来决定 ，and then beta value is fixed from this boundary condition. So you end up having a T mole resonant frequency given by this expression with 3 indices n, p, q. And again, n is the mole number along phi direction. P is the number of zero crossings associated with J prime n. Okay, and then Q is decided by the z boundaries along z boundaries. If you choose this to be psi q pi for the hz, this means that the minimum value of q has to be equal to 1. 你不能把这个q 带0进来，把这个全部杀掉。你如果把 hg 杀掉的话 ，T mole 就没有意义了。来 ，so the minimum value for q is equal to 1. Okay, and the minimum value of this 1 from this diagram, you know this is x prime 11 right here. So the minimum value of f is going to be TE111. Okay, so that is the dominant mole for TE. Alright, it is going to be a little boring that if you continue to calculate Q and so on, because all the steps are going to be the same. You want to write down all the magnetic field component and electric field component for the T mole based on this Hz field. 全部写出来之后呢，你再去算它的这个 energy 在里头啊，还有这个 power loss based on the surface current， 那你就可以算出 Q 的值出来。那你课本里头还算的还蛮多的，你看有不同的例子。Alright， 所以if we go back to the very beginning, a little bit review. We start from the tangle bus. We seal the space and allow standing wave to be inside and store energy inside. And then the excitation requires certain frequency. That is relevant to the capital Q. Okay. So this guy Q defines the bandwidth of the resonator. Okay. And also the decay time, everything about the quality of the resonator. 然后呢，再来就是把真正的这个场呢，把它写出来。那这些写出来方法都不是就是一些数学计算，而是用我们知道的物理的边界条件去把它写出来，所以速度还蛮快的。就是画上边界之后，你就 standing wave 在自己的方向，然后呢，想想看边界条件，然后就很快的可以写出你要的东西出来。Alright, so this is the pretty much I want to tell you about an electromagnetic receiver. Is there a question? 至少基本的概念都懂，来，是的。
好的，所以就是前面不是在讨论那个它的 bandwidth， 那 bandwidth 是指它可以接收能量进来的这个 frequency 的区间。那后面在讨论 cutoff frequency 的时候，感觉 cutoff frequency 对我来说很像是这些 field 可以存在的一个最小值，那它跟这个 bandwidth 有什么关系？
想象你在做实验。OK， 你有特定你要excite特定的 mode 出来，譬如说 ，for example， you pick the one cavity for your experiment, okay? So that's the pick one cavity for your experiment, and then you want to excite some mode inside for your application, okay? Now, so you think about one particular application. For example, you want to push electron along this direction. Then you'll be adopting, for example, this mode. Well, you have electric field going this direction, right? And then if you put one electron here, then you'll be pushed forward. Then you accomplish your application. Now you want to think about how you do this experiment. So you pick up such a cavity, and then you start to you want to pump energy inside. Now, practically, well, this is very practical. Okay. Now you pump electromagnetic wave like this inside. But how do you know how long I want to pump this electromagnetic wave inside so that this cavity reaches the maximum storage? The length of this pumping is roughly your filling up time. And this is relevant to Q. 所以 Q 会告诉你说，哦，我正在做实验的时候，我的这个 source 要激发它多久 ？OK， 那好，你在做实验的时候，你发现，哇，you pump it over such a time, but you don't quite build up the power inside. Then you realize that, hey, this frequency is not precise enough. The Q is given by this expression. So the frequency, well, you know the frequency of your wave, but you need to set your frequency within such a small value. 譬如说，the first thing is that you move the frequency up to the cutoff frequency, a little bit up, and then you want to excite this, right? So you pump it into, you say one antenna to put it into the cavity, and then you start to crank up the power. But then you found that the energy inside is not quite high based on this formula. Something is wrong. And then you go to check the frequency, 就是这个的精确度，发现没有达到这个标准，所以你能量还是灌不进去。So you have to go back to deal with your internal circuit to make sure your bandwidth is within such a value so that your energy can enter such a cavity. 所以这些都是很实际，你在做实验的时候务必要面对的问题。OK， 所以从 cutoff frequency 开始，第一件事情， 你的频率就要比这个 mode 的 cut frequency 高一些些。那你如果高的太多的话，你其他 mode 都会长出来。And that is not what you want. Okay, so think about this is a step-by-step experiment you want to accomplish something. 那所以我今天在上课之前，我到这里来的时候，还想说，我们好多的同学在学 circuit design， 在学这个programming 等等，那有点是这个 routine 的这种 practice， 那这些其实很快都会被 AI 取代掉。你如果只是做 routine 的 practice 的话，没有人的思考在里头的话，基本上AI 一个键帮你这个 program 写好了，或者是一个电路设计，你给它几个 instruction， 它就帮你设计出来。但是呢，你们不一样，你们了解这个 physical picture， 你了解做实验怎么做，你知道怎么做 presentation 的话 ，AI 没办法在这个短时间内就是把你们全部取代掉 ，OK？ 所以黄仁勋说最好赚的工作就是水电工，因为水电工不会被 AI 取代掉，或者建筑工。Anyway, I just want to tell you that in fact， 这里头知识可以是活的，所以活的意思就是说，你就去做实验 ，do your experiment. Then you start to think that hey, the frequency has to be higher than the cutoff frequency. And then, how long you have to pump the energy into a cavity? Well, if you know the Q, you know how long you pump the energy into, you have to pump the energy into the cavity. And then, if the things does not go well, then check the bandwidth of your source. If your source is not within the bandwidth, then the energy cannot enter. 所以就是有一步一步的这种很实际的问题，你要去把它做到位，能量才会进去。这时候呢，你要的应用跟效果就会出来。Okay, I hope I answer your question. Yes.
可是那个 F 代表应该是共振腔的resonant frequency， 它是一个定值嘛，就是你给一个共振腔，它就会有一个它的共振频率。
它有 mode， 也就是说它这个频率是的，事实上这里有 M、N、Q， 你给定 M、N、Q 就会有一个共振频率在那个地方。OK， 看你哪一个 mode 你要 excite 它，所以呢，你给定一个 M、N、Q， right here。M、P、Q 或 M、N、Q， 你就会有一个共振频率在那个地方，但是呢，你可以你在做 excitation 的时候呢，即使 a little bit off the resonant frequency, you still can pump energy inside. Okay. The bandwidth is defined by this the resonant frequency divided by the cavity. All right. I want to give you as much as possible, and I want to start the lecture a little bit, and then finally we have a quick quiz for you. I want to start the lecture on antenna because from my point of view, antenna is a very exciting topic, and you should really look into this. Previously, we always talk about the confinement of electromagnetic energy. So we have transmission line, we have waveguide, and then we have resonator, right? So that is confinement of electromagnetic energy. What if I want to spread out the energy? Then I need to rely on an antenna, and then spread out the electric field and magnetic field. Okay. So the basic concept is like this. You have a waveguide, you have a transmission line. We studied at the very beginning of the semester. But notice that for this transmission line circuit, we always confine the electromagnetic energy in a small area, in a small space. Okay. Now we want to understand how to radiate away, to send the electromagnetic energy away. And we need one antenna at the end of the network. OK， 所以你在做一个电路的时候呢，那些电路其实都是集中电池能量的东西，但是呢 ，antenna 呢是要把电池能量送出去、扔出去，所以呢，你不要它基本的概念跟 waveguide 跟 resonator 等等的话是不一样的。你要把那个 electric field 送出去，让它进入开放空间。And usually we want to send the energy, the electromagnetic wave over a long distance, very long distance. So here in front of me, this is sort of an antenna rod, but from a person located 1 kilometer away, this is just 1 point in space. Okay, if you look at this antenna from 1 kilometer, 10 kilometer away, this is just 1 point in space. So we'll be adopting the spherical coordinate system to describe the behavior of the radiation. So the three important position variable is going to be R theta phi. Okay, so this is basic concept. And so on this slide, I told you 2 important concepts. Number 1, for a circuit that has a purpose to confine the electromagnetic energy, and for antenna, the purpose of antenna is to spread out the energy. Okay, and the second concept is that they will be adopting the spherical coordinate system for the discussion of antenna. Now, your textbook always give you some mathematical steps to solve the problem, and my emphasis for this class is the physical picture. So if you can combine the 2 strengths of the discussion, then I think you'll be in good shape of learning. All right. So the first thing is that you have some current inside this antenna, and this current will allow you to calculate the vector potential. Okay, you have done this before, right? And once you have the vector potential, you'll be able to calculate the magnetic field based on this curve A iteration. Once you have the electric field, a magnetic field, then you can connect the magnetic field to the electric field from this coupling of electromagnetic field. So those are the step 1, 2, 3 for you to calculate the electric field, magnetic field for this antenna problem. Everything starts some currents in the antenna, and then you have magnetic field, electric field, and of course you want to understand how you send your money around. That is how you send your power into the space. And you'll be expecting that this is a function of R theta phi. Okay, R theta phi. So this is the basic 1, 2, 3, 4 steps for you to analyze an antenna problem. Okay, is this good, simple enough? 特简单 right? 所以呢 Hertzian dipole 的话 basically starts from a very small antenna that is much smaller than a wavelength. So you have uniform current on this. Okay, 这是一个 antenna. 然后呢，你的波长，你辐射的波长远大于这个，所以这是一个什么？这是一个 long circuit， 或是一个 transmission line circuit。long circuit 的意思就是说，你的这个电路的 dimension 远小于你的这个电磁波的波长，所以呢，所有东西你不需要太考虑它的相位。同样的，在这上头的话，我们不考虑电磁波在这上头的相位。Okay, just treat as a uniform current oscillating with time, but there's no spatial dependence on it. And then we try to understand the radiation behavior of such an antenna, and we call this Hertzian dipole. This is simplest dipole because you don't need to consider the phase, the current phase on such a dipole. Okay. 那这里头呢，就一连串的还算简单的这个概念。那我想你应该是在这星期3的 review 的 question 里头会去做一些预习，好不好？所以我们星期3的话，会给你有一点时间做一下 presentation， 但是会持续这个电池天线的一些介绍。 Before you go away, I think we have 5 to 10 minutes to do some simple practice. Okay. 我们有这个 direction web guide for more number 的这个理解，应该很快。可以聚焦慢慢教。这个 quiz 的话，就是让你很清楚的对应到 M 跟 MO 跟 MB 的数值是之间的关系，所以连接第一个lecture 的